The range of a linear transformation is defined in the usual sense, no? For functions, it's the set of all vectors in the codomain, okay, that are images under L of vectors in V. Okay, so it's the set of all vectors in W such that L of V equals W for some vector V in the domain. Okay, so the range is usually denoted by ran L or L of V. So this is nothing new. No, we already know this notion of range, no, for functions. So we are using the same definition for the range of a linear transformation. So going back to our linear operator earlier, so we observed that the vector 3, 0, negative 3 belongs to the range of L because 3, 0, negative 3 is the image under L of 1, negative 1, 2. 1 plus 2 equals 3. 1 plus negative 1 equals 0. Negative 1 minus 2 equals negative 3. But 1, negative 1, 2 is not in the range, of L because suppose xyz is a vector in R3 that is mapped by L into 1, negative 1, 2. Okay, then 1, negative 1, 2 should be equal to this vector with components x plus z, x plus y, and y minus z. So this is a system of linear equations, no? Given by x plus z equals 1, x plus y equals negative 1, y minus z equals 2. You can solve that and show that the system has no solution. Okay. Actually, if we take the difference of the second equation from the first, okay, we'll get y minus z equals negative 2, which contradicts the third equation. This system has no solution, justifying this claim that 1, negative 2, 1, negative 1, 2 is not in the range of L. How do we compute, or so how do we describe all the elements in the range of the linear transformation? So observe from the definition of our L that the image of xyz under L can be expressed as a linear combination of three vectors. Okay, x plus z, x plus y minus z, y minus z can be expressed as the sum of the scalar multiple of 1, 1, 0 by x with the scalar multiple of 0, 1, 1 by y with the scalar multiple of 1, 0, negative 1 by z. Okay. So you can verify, no, that this works out. Okay, so the point is L of xyz is a linear combination of these three. Because xyz is arbitrary, we see that the range, of L is the span of these three vectors. Okay, because every element in the image is a linear combination of these three vectors. But note that this is not a basis. The third vector is a linear combination of the first two. Okay, 1 minus 0 equals 1, 1 minus 1 equals 0, 0 minus 1 equals negative 1. So this third vector we can take that out of the set. So actually, we only need 1, 1, 0 and 0, 1, 1 in the spanning set. And you can check that these two vectors are linearly independent. So this actually forms a basis, for the subspace spanned by these two vectors. And that's it. This subspace of R3 is the range, rather, It's the range of L. So in particular, we see that the range of L is a two-dimensional subspace of R3. The kernel and range of a linear transformation are important objects associated with L, and these objects encode information about the vector space V and W. So we already noted that if L is a linear transformation, then the kernel is a subspace of the domain, while the range is a subspace of the codomain. So I will leave as an exercise the proof for these statements. You may just apply the subspace test. So because kernel and range are subspaces, well, they have dimensions. Okay. So suppose that V and W and are finite dimensional vector spaces. The dimension of the range will be called the rank of the linear transformation, and denoted by rho of L. On the other hand, the dimension of the kernel will be called the nullity of L, and denoted by eta of L. So you might remember that earlier we defined the notions of rank and nullity for a matrix. Okay, this time we're defining rank and nullity for a linear transformation. Okay, later on we will see that this definition is consistent with the um, definitions of rank and nullity that we defined for matrices. And with that, we also have a rank nullity theorem for linear transformations. Okay, so if L is a linear transformation whose domain is finite dimensional, then the rank and the nullity of L sum up to the dimension of the domain. So for instance, in our illustrations earlier, we considered this linear transformation from R3 to itself. So V and W are both equal to R3. We computed that the rank, or rather the kernel, of this linear transformation is the subspace spanned by 1, negative 1, negative 1. Okay? So the kernel, or rather, moreover, we proved that the image, moreover, we showed that the range of L is the subspace spanned by 1, 1, 0, 0, 1, 1. This is a basis for the range of L. So in this first line, we see that the kernel is a subspace of V with dimension 1. So the nullity, eta of L, the dimension of kernel L equals 1. And the range L of V is a subspace of the codomain with rank rho of L equal to dimension L of V, which is equal to 2. And we can verify the statement in the rank nullity theorem. The sum of the rank and the nullity of L, 1 plus 2, is equal to the dimension of the domain, which is 3.